Hey there, awesome Science 2 kiddos. Going to use these slides to review the first two sections of Hewitt chapter 26, introducing you to the atmosphere. The atmosphere is just a very thin layer of gases that gravity is holding to the surface of the Earth. The reason I have a picture of a bowling ball here is because if you think of Earth as that bowling ball, the atmosphere is about as thick as the kind of enamel plastic sheen that's on it. So it just shows you again how thin it is compared to the overall size of our planet. We'll delve into this more later, but we can describe the day-to-day changes and conditions within our atmosphere. That is weather. Again, very temporary, right? Whether it's raining one day or sunny the next, specific to a particular time and place. Climate is more general, right? So climate describes patterns in weather for certain locations, right? And climate can, weather can change. Climate can also change, but climate change is definitely more gradual. Whereas weather change happens again, you can have multiple forms of weather within a single day or 24-hour period. Now, there's a lot of different spheres that we consider when looking at Earth. You can look at the biosphere, which is where living things are and interact. We'll be learning about the lithosphere later and some of the inner layers of the Earth. But what we want to focus on right now is the atmosphere and what's going on with the different gases, and we'll tie that to the biosphere then. So Earth's atmosphere, as was covered in some of our early solar system presentations, is actually mostly nitrogen, about 78% nitrogen gas. That's actually N2. It's a diatomic molecule. It's completely innocuous. It's not flammable. It's not poisonous. So it's actually a good thing to have in the air around us, right? It prevents explosions from getting totally out of control. We're not going to suffocate from breathing it or anything like that. 21% of it is oxygen, and that's what's really important to us. O2. We use oxygen to produce ATP in our bodies. It keeps us alive and functioning. But we want to keep that percentage relatively low because then you're also not going to have, anytime you flick on a lighter or something like that, you're not going to have a huge explosion because oxygen is actually very flammable and very volatile. And then you've got a very, very tiny percent of other gases make up about 1% of the rest of the atmosphere. That's everything from carbon dioxide to water vapor. Carbon dioxide levels are definitely rising. I don't think percentage-wise it's been a huge contribution yet, though it is getting there for sure. So let's now look at layers of the atmosphere, but before we get into that, you got to understand something about pressure. So air pressure, think of it as, you have to constantly think of air as being full of molecules, right? I like this little image down here. And you can feel these, right? If you wave your hand around in the air, you can feel the air that is around you. Those are molecules that your hand is colliding with and moving. And those exert pressure on the surface of an object by colliding into it. We don't think of air as having weight, but it does, right? It's very minuscule, it's not very much of it, but it definitely is present. So the pressure inside of our bodies is equal to the outside pressure. We are evolved to be living at sea level or thereabouts, right? But there's changes in air density as you go up. So, and this diagram shows that, right? You can see down here, molecules are very packed together, whereas higher up here, higher in altitude, they tend to spread out a little bit more. And that's purely due to gravity, right? Earth's gravity is pulling these gas molecules towards the center, just like it pulls any other object. So again, good way to think about it too is to imagine if I was somehow able to stand on this curve here in this graph, little stick figure here. You can see that I've got all of these sort of units of air on top of my head. Again, I know it's a weird thing to think, but that's exerting pressure, right, on the body at sea level. And then if I were somehow able to travel to a higher altitude, I'm going to be experiencing less pressure because there are less of those sort of squares of gas or air on top of me, right? This is very similar to like being in a swimming pool, right? We are comfortable at the surface of water. If you dive down deep into a swimming pool, you have a lot of water suddenly weighing down on top of you, and it can exert pressure on your ears and things like that. Those are the ways that you feel it. So think of air pressure sort of like that. I know it's a little unusual. Now, Bob Gardner, I'm just showing you where his balloon reached. He got to about 39 kilometers high. We'll put that in context soon. Again, this is just a demonstration showing that relationship again between internal pressure and external pressure. These have to equalize, or what's going to happen eventually is if, as for example, as you go up in altitude and this external pressure lowers, then that means that comparatively the internal pressure will be a little bit higher. So for example, a balloon like this that was going to rise in altitude, As the external pressure lowered, this balloon would inflate or expand, right? It would get larger in size. And that's what happened with Bob Gardner's balloon. If you watch the video closely, you can see that the balloon is barely inflated when he first takes off, but then towards the final end of his video, this is what it ended up looking like. This is number 5 right here, the actual Stratus jump. So they have to account for that expansion of gas because there's less external pressure once you're that high up in the atmosphere. And the balloon's usually made of pretty tough material, but very thin material as well to keep it light, so there's not too much weight. Okay, so let's talk about the layers of the atmosphere very briefly. The first one, which is right on the first layer, which is where we live, it's where the biosphere is the troposphere. This is the important one to living things. It's closest to Earth's surface. It's a thin layer, but it's very dense. Quite a bit of the gaseous molecules are located there because, again, gravity's pulling them downwards. Temperature and density decrease as you rise in altitude, right? So it gets colder, as you know, right? If we climb to something tall like the top of Mount Everest, which is pretty high up in the troposphere, it gets a lot colder. The next layer is called the stratosphere. It's a much sort of thicker. Again, it's about 12 to 50 kilometers makes up that elevation. And the unusual thing is that temperature increases. We saw this with Bob Gardner. Now, it's still cold. It's still below freezing, but it gets warmer, actually. And this is because of the gases that are present. There's some CO2 present. More importantly, this is where you see the ozone layer, the O3, which can absorb solar radiation or heat from the sun really well. So it warms up the gases that are present. Again, it's still below freezing, but you're going to see an increase in temperature from where you started lower down in the stratosphere. Now, Bob Gardner made it that high. So he was in the stratosphere. That's why they call it the Stratus jump. That's where he jumped from and returned back to Earth. So this graph is a little unusual, but it's kind of similar to the one you made, but it's flipped. So here's altitude on this side, and then here's the change in temperature. So this weird looking red line is just showing you that it gets colder as you rise up in the troposphere, colder, but then it gets I shouldn't say warmer, it gets less cold as you then move through the stratosphere here. And again, this is where the ozone layer is. The mesosphere, you can see temperature drops drastically again, and then, and I'm not entirely sure the reasoning behind this, but once you hit the thermosphere, then temperature drastically increases. And again, I think it has to do with the gases that are present there. So the mesosphere accounts for about 50 kilometers to 80 kilometers of that level of elevation right here. Bob Gardner did not make it into the mesosphere just because the balloon probably wouldn't be able to rise much farther. It wouldn't be buoyant after that point. The air gets so thin. There's no solar radiation absorption here, so it's very, very cold. I guess there's just aren't gases present. But again, not entirely sure then why you see such a spike in temperature. I mean, this is pretty extreme in the thermosphere, but I mean, the name thermo does mean temperature or warmth. I think it probably has to do, again, with the gas content that's present there, that and proximity to solar radiation, right? This is where solar radiation is first arriving, and so I think a lot of that gets absorbed by those gases before it can make its way to those lower layers. So it's sort of taking a lot of the heat for the layers below it, I guess is a good way of thinking about it. Okay, you have already read about this, so hopefully this was just helpful review. Thanks.